All right, so in this problem, we're having an alkene addition, right? We're adding HBr. So as a reminder, when we add HBr, anytime we have an acid and an alkene, like we do here, alkene is always going to grab the proton. And then so now, whenever I'm adding across a double bond, my hydrogen can go to one of two carbons, right? So which carbon is going to take the proton? Carbon 1 or carbon 2?
1.
2.
2. Because remember, if carbon 1 takes the proton, so if 1 gets the proton, 2 becomes the carbocation. If 2 takes the proton, 1 becomes the carbocation. So which one is going to be the better carbocation? 1 or 2?
1.
1 becomes secondary, right? So you always want the least substituted carbon to take the proton and the more substituted carbon to become the carbocation. So we should now have this. And don't forget, we need to have our charge. And we have bromine like that. So now, what's going to happen? Does our bromine add straight to our carbocation?
No, it's going to do a shift, I think.
Yep, because there's two clues here that's going to help you, because this is the carbocation right now, but in your product, that's not the carbon that has the bromine on it, right? Also, again, when you form a secondary carbocation next to a tertiary, you always have a hydride shift. Don't forget that. So once you have that hydride shift, you then, this is your carbocation here. So then your bromine is going to attack, and then that'll give you your final product. Does that make sense? Questions on that?
I have a question about something else.
Mm-hmm.
So a hydride shift is when a hydrogen takes the place of the carbocation, and a methyl shift would be the same thing, just a methyl's moving?
Yeah, so basically the way to think about it, right, is that when we have a hydrogen like this, we actually have 2 electrons there, right? So we say that the bond is moving over, but in reality, the hydrogen and the 2 electrons are moving over. So like the whole thing is just jumping. Same thing with the methyl.
Okay, thank you.
Yep. Questions on this one? Are you guys good? How'd you guys do on that one? Better?
Yeah.
Excellent. So let's continue on. Draw the mechanism for the following reaction. Show all non-zero formal charges. Show all reaction intermediates. Use arrows to show electron movement. Include stereochemistry. So dihalogenation. Okay, so in this type of problem, we're doing a dihalogenation addition, right? We're adding 2 halogens across our double bond. So the key here is that we know that we are going to add both of these halogens, but this is a little bit different, and you just have to kind of pay attention to it. So like I said, it's easy if you draw out the Br to Br. And also, I recommend always draw all the lone pairs on an atom when you're doing your mechanisms, but in this case, you really only need to draw at least one on your bromine like this. So this is a weird mechanism, all right? What is going to happen is that your bromine is going to attack one side. At the same time, the double bond attacks it like that, and then you're going to break off like this. You guys don't look happy.
That looks weird.
This is what happens because your hydrogens are going to go back, right, on top. They're both going to be dashes. And now you're going to make this wonderful little intermediate, a brominium ion. And then on the side, you have a bromine like this. Have you guys done the mechanism this way? Does this look familiar at all?
Yeah.
Okay. This is when you do these mechanisms, when you have that bromine, the double bond is going to grab one of the bromines, and that same bromine is going to come back and attack the other side, and then you're going to break that bond. So imagine you're just going like in a loop, like that, right? It's just going through, it's a loop, okay? So now in your last step, this comes in, break it off like that, and then that gives you your product. So you only have 2 steps in this mechanism. One, you attach the bromine across both double bonds, you make that thing called the brominium. In the second step, the other bromine comes and attacks from the backside. And that'll give you your product. Morgan, you don't look happy. But that could just be a general phase.
Yeah, it's just like, it's kind of confusing with all the arrows, but I just got
Okay.
soaked in.
All right. Can I erase this? Are you guys good? Because I'm gonna go into more definition. So what happens is that when you have this, like this, lone pair comes and attacks one carbon like that. Well, attacks one of the carbons. The double bond is going to come up like that. So imagine a loop like that with one bromine. Okay. At the same time, this bond is going off onto this bromine. It's going to pop off now and fly off. So when a double bond attacks an atom like that, that means that one of the carbons is going to form a bond with that bromine. And then this is going to come down and form a bond to the other side. So then that's how you end up getting this 3-membered ring, which is called a brominium ion. It has a plus charge like this. That's what's happening in that first step, if that helps you a little bit more. So as you guys learned earlier this semester, are 3-membered rings stable? They are not. They are extremely reactive, which is why this bromine can then come in and pop off like that. The other bromine will come in and attach. And this is also why your bromines are always facing opposite directions. They add anti, because your bromine adds one way, the other bromine has to attack from the backside. Make sense?
Because it was on the wedges when it was a brominium ion?
Yep. If they could have been on wedges or dashes, whatever, it's just that whenever you have this type of reaction like this, and if I do bromine or chlorine or something like that, when you have your products, you will always have one on a wedge and one on a dash, or in this case, they will be literally pointing in opposite directions like that. So you can either draw them pointing in plain opposite directions. You can see this bromine's pointing down, this one's pointing up, or you can have a bromine on a wedge and a bromine on a dash. It doesn't matter. Both of those are implying the same thing.
So those are both equal?
Mm-hmm.
And is that because if you twisted the top one in the box, it would just look the same?
Yep.
And that's the only product you can get from that?
Yeah. Well, you can get your bromines on different, so imagine if you had like two on the, like one on the wedge, one on the dash, you could flip them so that the other one's on the wedge and the other one's on the dash. There's no stereospecificity. It's just that one will always be pointing one direction, the other one will always be pointing the other direction. They will always be anti-directional. They are anti-addition. Does that make sense? So Morgan, how many steps are there in this mechanism whenever you add BR2 across the double bond?
2.
Always 2 steps. So if you remember that, that should at least help you, right? So sometimes people get a little stuck in the arrows, and that's fine. But as you start memorizing them, if you remember that this is just a 2-step reaction, you can at least say, I know there's at least 1 step between here and there, and that'll help you out. Okay, again, this is where flashcards come handy. Okay, so let us work through this again. We'll do what we did yesterday. Yesterday, what we did is that we walk through these and we talk about how to solve these. So in this problem, it says predict the major product formed in each, indicate if the reaction undergoes SN2, SN1, or E2. So right off the bat, we don't have to worry about E1. So that takes a little bit of heat off of us. So what we talked about so far is that when you are trying to identify your type of reaction, Gwen, what's the first thing you should do?
Identify what kind of carbon it is.
Yep, find the carbon with your leaving group and identify what type of carbon it is, meaning is it a methyl, primary, secondary, tertiary? So this is my carbon with my leaving group. What type of carbon is that?
Secondary.
Secondary. So secondary, unfortunately, does not eliminate SN2, SN1, or E2. All are still viable. All right, so that doesn't help, but that should always be your first step. Next step, I take a look here. What type of reagent is that? Weak base, strong base, weak nucleophile, strong nucleophile, some combination?
Strong of both.
Strong nucleophile, anything else, or is that it?
Strong nuke, strong base.
Yes, so remember, I know Magpie and Gwen and Matthew, I know you guys know this. What is unique about ETO minus an Na plus? What are the other two?
There's NaO and
MEO minus and Na plus, and HO minus and Na plus. Sodium hydroxide, sodium methoxide, sodium ethoxide. They are the only 3 that are both strong nucleophile and strong bases. Meaning these are the only 3 reagents that will ever tell you that an SN2 or an E2 is possible. Those are the only 3 that will ever have this conundrum. But if you run into this problem, Gwen, because I know Gwen's on top of it, and you're like, well, this is one of those reagents that Dr. B has hammered at us countless times, and I know that E2 and SN2 is possible. How can I distinguish between E2 and SN2 looking at the arrow?
Because there's heat there, and so it's automatically going to be an elimination reaction.
E.
Yep, when you have heat, that forces the elimination reaction. Heat will make you think this is going to be the E2 reaction. Does that make sense? So those 3 reagents right there, those SN2 and E2 are possible, but the second you start having heat, that means that that is going to be an elimination. Now, ethoxide, small base, big bulky base.
Small.
Small. What were the 2 keywords we said to look out for if it was bulky?
Iso and tert.
Terbutyl.
Tert-butyl or isopropyl, maybe even something like cyclic or something like that, if it's a big group. But ethoxide is a small base. So if it's a small base, do we do Zaitsev or Hoffman? Zaitsev, we take from the most substituted carbon, which is also the carbon with the least amount of hydrogens. So we are going to take our proton from there. So our product should simply look like this. I guess if you wanted to draw it in the chair conformation, it's wrong to draw it this way, but if you just want to draw your double bond like that. That is very wrong. That is a very incorrect drawing, but just for this, the simple sake of saying, let's draw this as it's presented to you. Like that. Morgan, did that make sense for how we walked through that one?
Yeah.
Okay, so now Morgan, let us talk about the next one. What type of carbon is my leaving group attached to?
Two secondary.
Yep, it is a secondary. So does that eliminate anything, or are all three still open?
Still open.
Okay, they're all open, but now I take a look at my reagent. Strong base, strong nucleophile, weak base, weak nucleophile.
Both strong.
Nope.
Oh,
Because what's the difference between this one and the one above it?
there's a H, so it's a weak.
It's neutral, right? When it's neutral and it has that H, it is going to be weak. So if it is a weak base, it is also a weak nucleophile. Normally, I have to worry about SN1 and E1 competing, but do I have to worry about it in this problem? No, because you only have these three. So it is simply going to be a substitution. Is this carbon currently a stereocenter? Nope. So I don't have to worry about two answers, and it's not next to a tertiary. So I'm simply going to get one product like that. That's going to be it. I just substitute. Does that make sense?
You said this is SN1, right?
Uh-huh.
Okay.
Yeah, because it's a weak nucleophile, right? Okay. Let's go ahead and go to the next one. So again, this is secondary, right? I look at my reagent. What type of reagent is this? And if anyone wants to hazard an answer.
Is it a strong nucleophile?
There are three people on this call who should have it right. And Gwen, you are correct. Remember, if you have a sulfur minus, a sulfide, S minus is always a what? You just told me.
Strong nucleophile.
Always a strong nucleophile. S minus makes a fantastic nucleophile. So strong nucleophile. I have a secondary carbon, and my solvent is polar aprotic. So which reaction is happening? SN2, right? Strong nucleophile, polar aprotic solvent, secondary primary methyl carbons in play. This is going to be an SN2. This is also my advice to you, Cole and Morgan. When you are taking this test on Friday, I know you guys are going to ace it, but just to be safe, always write what type of reaction is happening. That way, in case you make a mistake, at least whoever's grading it can say, well, they knew what they were doing, and if there's partial credit, maybe you might be able to get yourself some partial credit, right? Because sometimes that partial credit's the difference between an A and a B. So do everything in your power to demonstrate that you know what's happening, even if you make a mistake. So in an SN2 reaction, if you remember, do my other stereocenters change? Or do they stay the same?
No, they stay the same.
They stay the same because chemistry is not happening there. What about this stereocenter? Do I get two products or one product in an SN2?
One.
I get one product in an SN2. I invert my stereocenter. So now this is just going to be a dash SCH3. Because remember, we attack from the backside attack. Questions on that? Okay, I'm gonna let you guys do the next two on your own using that same bit of logic we just used. I'll give you guys a minute or so, and we'll see what you get. Okay, so let's take a look at this problem. So what type of carbon do I have?
Primary.
Primary.
All right, does that eliminate SN1, SN2, or E2?
S and 1.
Yep, you eliminate SN1. You would also eliminate E1 if it was a possibility, because remember, you can't do SN1 or E1 on a primary carbon. All right, so now I have SN2, E2. So now, is this a base or a nucleophile?
A base.
It is a very strong base. Tert butoxide, right, is this. It is an oxygen attached to a tert butyl group. It is very bulky. It is very large. It can only ever be a base. But since it's a base, what reaction is happening?
E2.
All right, what else is telling you that E2 reaction is happening?
The heat.
The heat. That's your other clue. Remember, heat always favors elimination reaction. So normally with a bulky base, you might have to worry about the Hoffman product, but is that an issue here?
No.
Because you only have one beta carbon to my alpha carbon, right? So my product is simply going to be that. Questions? Okay. For the last one, I'm just going to draw the product and we'll see how angry you get. Secondary carbon, weak nucleophile, or a weak base, right? But we don't have to worry about E1. So the only reaction that can happen is SN1. First step that happens, leaving group leaves, I form a carbocation. But I have a secondary carbocation next to a tertiary carbon. So what has to happen? Hydride shift. Now I can add my nucleophile. So then that's going to be the product. Is that what you guys got? Gwen, where'd you mess up?
I just didn't do that at all.
Okay. But does that make...
But I get it now.
Okay.
Why can't you make it a hexane or a cyclohexane?
You could do that too. So I'm gonna pop to the whiteboard just to say you could also get this, because you also had earlier on the exam. This is probably going to, now thinking about it, you're right. This is probably the product you're going to get, because this is what you had earlier on your mechanism page, right? I think it's pretty much the same problem, the same type of problem you had on the other one for your mechanism. So is this what you got?
That's what I got.
Yep. That's probably the better answer there. Remember, always listen to what Dr. Dewis tells you, because she is your professor. I'm just a handy organic elf that is helping you. Okay. Predict the major products or give the reagent for the following reaction. So I have H2O and H2SO4 with an alkene. So when I have an alkene, should I think elimination or addition when I start with an alkene?
You get rid of the double bond.
Yep, I'm going to be an addition. So my product here should be this. So right now I'm telling you, these alkene additions you need to have down. These are memorizations, right? Mechanisms are important, but flashcards for these are going to be important. So what's our next type of reaction? Do you guys remember what this one's called? Or what it does?
Isn't it the hydroboration?
Yep, hydroboration. What are we adding?
OH.
All right. Do we add it to this carbon, inside carbon, or outside? The more substituted or the less substituted?
More.
Less. Hydroboration is my anti-Markovnikov. The OH is going to go to the less substituted carbon. This is the only addition reaction with alcohols where it goes to the less substituted. Your key indicator is boron. Boron is a weird element. questions on that one? Okay, again, these are the ones that you need to have memorized because mechanisms are important, but when you get to these types of problems, these should be the ones that you can just fling out as fast as you can. Make flashcards. Flashcards will save your life, particularly those of you that have to take organic 2. All of these reactions are going to come back flying at you.
I have a
Okay,
question.
yes.
So for the one we just did, if we had a chiral center,
You
or
could-
yeah,
You would get
can you get
2
an
answers.
enantiomer?
Yep.
Okay.
Next question. What are we getting here? What are we adding?
OH.
We're adding an OH. This is an oxymercuration, except now, what's the difference between the last one we did and this one?
You're gonna add it to the more substituted side.
Yep. When you see boron, you're adding OH to the less substituted. When you see mercury, you're adding it to the, sorry, when you do the hydroboration with boron, you're adding the OH to the less substituted carbon. When you're doing the oxymercuration, you see mercury, you are adding it to the more substituted side. So in this case, again, you can also get this one wouldn't matter. So you could get like this plus the enantiomer where you flip those. So your other one would just be like that.
If you, instead of drawing it out, if you just
Wrote
say
enantiomer.
EN, yeah, is that wrong?
If Dr. Dewis is fine with it, then do it.
Okay.
Remember, that's for me. If I was grading your test, I think I would be fine with it, but I'm not grading your test. Remember, this is not my rodeo. And remember, if you ever tell Dr. Dewis that I said that you used the phrase Dr. V said we can do this, what will I tell? How quickly will I sell you out? I will sell you out so
Very
quickly.
fast.
Yes, I will sell you out very quickly. And it's
I
not
never talked to her anyway, so, and I would never tell her.
okay. It's just because I once had students that I helped out, and one of the students went to the professor and said, "Well, this is what Terry told us." And I went to the professor and I said, "Hey, I was just helping him." I said, "Talk to you," but that's just that. Okay. So what is happening between our starting reaction and here?
Something with ozone, maybe.
The
Yep.
O3.
Yep.
And the
O3 is
DMS.
ozone. Yep. O3 and dimethyl sulfide. Because essentially you're cutting it, right? This is a cleavage reaction. You're just cutting that double bond. Does that make sense?
What does the DMS do?
Essentially, if I use DMS, I will form an aldehyde this side because there's a hydrogen right here, right? And there's a CH3. So this CH3 is this CH3. And this hydrogen is this hydrogen. If I use something like peroxide H2O2, that H will become an OH. So it just depends on what my final product will be. I'll still cut it, but it just determines whether I get aldehyde or carboxylic acid.
Okay.
So if she hasn't told you about that, it just basically finishes the reaction. You form this 5-membered intermediate, and so when you cut it, that DMS helps you break that. It's fancier mechanism stuff that you don't need to worry about. Well, at least I don't think so. I don't know. I haven't seen anything. Okay, what are the products in these multi-step synthesis? So I will give you guys 1 minute because these should be fast ones to do the first one. Okay. So in step 1, we have an alcohol, we have concentrated sulfuric acid and heat. What type of reaction are we going to do?
Elimination.
Yep, it is an E1. When it's an alcohol and sulfuric acid, it's an E1 reaction. Just file that away under your headspace somewhere that it's an E1. So we are going to form a double bond. Now, which way is the double bond going to go? To the right or to the left?
To the right,
Why isn't it going to go to the left?
because it would be a Texas carbon.
Yep, there are no hydrogens here anyway. You can't take a proton from there. You can only take a proton from this side. So our double bond is going to go to the right like that. There are no beta protons. All right, and then when we do BH3, Morgan, what functional group are we adding when we do BH3? We just did it up there, if you remember. What type of functional group?
I don't know.
It's an OH. So when you see this, know that we are adding an OH to it. And again, just to double check, are we adding the OH to the less substituted or the more substituted?
The less.
The less, right? So this is going to be an OH on that side. Does that make sense? So when you see BH3 THF, know that you are adding an OH across a double bond. Remember, benzene rings do not react with any of the chemistry you have learned so far. Even though it looks like it has those double bonds in there, it is something completely different, right? We only care about double bonds and chains, not in the rings like this, not in the benzene ring. Does that make sense? So this is in your alkene PowerPoint. All right, time's about to finish up. So I'm going to close this real quick. We'll come back, and I think this will be our last one when we come back because I think we're almost done with the tests. Be right back.